Okay, so for the final lecture, we'll kind of look at how to apply and actually modify and then apply some of the methods that we've been talking about to different engineered situations. So as we've kind of motivated at the beginning of the first lecture, there's increasing interest in these kind of multi-agent systems where you have a distributed decision architecture of many components making decisions and working together. So it's a departure from the traditional, I'm sorry, it's on mute. Yes, it is. It's a departure from the traditional architecture of controls where we have a single decision-making control system, and we have many controllers interacting with an environment. And the connection to games was that the quality of a decision of one agent, it depends on the decisions of other agents. Now, if I had to pick one feature, it would be distributed information that makes these kinds of problems hard. That each of these decision-making components has different information than the other decision-making components. If they all had the same information at the same time, then you could recreate this architecture. So my main point here is that just because something is multi-component doesn't mean that it is distributed as a design challenge. Again, if you had a coach controlling every player by strings, then it's multi-component, but there's one player that has all of the information. Just because neighbors are talking to neighbors also doesn't make something a distributed problem. For example, if we all, a simple illustration is if we all think of a number, and if we just gossip with our neighbors, then only by talking to neighbors we can find out what's the maximum number in the room. You don't have to gather all of the information and then have one person look at it and then announce it, but rather we just talk to our neighbors, say what's your number, what's my number, which one is larger, and we can just gossip that information throughout the room. So neighbors talking to neighbors doesn't make something distributed. Really, it's the distribution of information. And if information is costly to disseminate, either in terms of time or energy or what have you, then we're looking at a distributed decision architecture. So we're going to take the game theoretic perspective. And if you recall, a game has three elements. There's who are the players, what are their choices, and how do they have preferences over these choices, typically expressed in the form of a utility function. Our departure here is that the choices and the preferences are going to be design, a part of our design. So we're not looking at a system and modeling it and getting insights of the situation. Rather, we're designing these parts to a desired effect. And also, we talked about different types of evolutionary dynamics. So yesterday, we named best response with inertia. We talked about fictitious play, and we talked briefly about no regret dynamics. And they have different properties in different situations. Well, we're allowed to modify these dynamics to suit our needs, and that's also part of the design question. So the question is, if we have a desired overall behavior, can we design the game and design the dynamics so that we have so it produces the behavior that we want? The appeal is, here I'm writing distributed self-organization. Actually, self-X is now a keyword. If you look up self-X, there's self-organization, self-configuration, self-healing, self-what have you. So self-X has become a keyword, and it has that appeal of you put just some simple rules and they will organize themselves into what we want to see. If there's a change in the environment, then they will readapt to evolving environment. If there's a disruption, then they can, again, reconfigure to work their way around the disruption. At least this is the promise, okay, that we're after. We're not saying we deliver on all of these aspects, but that's the promise of having many simple agents perpetually adapting and evolving to achieve a desired effect. So what are the kind of the elements, again, to recall? We have a group of agents. These agents have choices. As system designers, we're interested in some overall objective, and this overall objective depends on two things. It depends on the actions of these agents collectively, but it also depends on some underlying environmental parameters, and we're just going to lump all environmental parameters into the symbol theta, and I'll say what the environment is in different settings. Now, what is our game theory playbook? The playbook goes as follows. Define utility functions, implement some adaptive learning rule, see what happens. Okay, that's the playbook. And we have some analyses to support a prediction of what will happen, but that's the playbook. And it depends on what information is available to the agents. And I'll talk about information in a moment. And then how are we going to judge the quality of this approach? Well, if we have a global objective, we'd like to see what's happening to this global objective as time goes on. But there are other factors as well. There's lots of other factors that we won't be talking about, and they're hard to talk about, in fact, of how fast does it reach, if it's behaving well, how long does it take to get there, what is the processing that each agent has to do, how much communications are going on between agents and things like that. So I'm going to start by commenting on other people's work that I mentioned yesterday, just to illustrate this playbook. What's the playbook? Define a utility function, implement an adaptive learning rule, hope for the best. That's the playbook. So if you recall this setup, it was a medium access game. We have nodes that are transmitting. They're sharing the channel. When there's an edge between two nodes, they can't transmit at the same time, or otherwise there's a clash, there's interference. And the environment is the underlying graph. The nodes don't necessarily have a global view of what does this graph look like. They just know that when they transmit, did a collision occur or not. And that depends on the other nodes. And with the nodes, their choice set is a probability of transmission. So day by day, they're deciding whether or not to transmit based on this probability. They need to decide what their probability will be. Well, in this paper, what the authors did is they set up, let's go through the playbook. First of all, they designed a utility function. The utility function has two parts. One part is to incentivize transmission. A is the probability of transmission. So you can think that, for the most part, bigger is better. There's some incentivization of transmission, okay, through this incentive function. This other part, it depends on my probability of transmission and the probability, a collective probability of transmission of everybody else. Well, not really everybody else, it's everybody in my neighborhood, but we'll just lump it as everybody else. What is this term? This is the probability of a collision. So I want to maximize my utility of transmitting, but I have penalized by probabilities of collisions. That's going to make me back off. This is the overall utility function of the incentive minus the collision probability. What they do a learning rule that we didn't talk about yesterday. They do what's called gradient play. So you know gradient, the gradient search, right? You just move in the direction of the gradient. They're moving in the direction of the gradient, but remember, they don't control, a node doesn't control a minus I. The node only controls a sub I. So it's moving in the direction of a sub I, okay? As though a minus I is constant. It's treating the rest of the world as a constant and moving in the direction of the gradient of the part that they can control. So their new probability equals their old probability plus a step size times, this is the gradient of their overall utility function, okay? Which is the gradient of the first part with respect to AI, and then the gradient of the second part with respect to AI, which is this term. Now, what is this term? This term is the probability that somebody else transmitted. How are we going to know the probability of somebody else transmitted in my neighborhood? I don't know it. If I had their transmission probabilities, then I would know it, because I could compute it. But I don't have it. So what are they going to do? This is an estimate. Sitting from where I'm sitting, I can listen for a while and figure out day by day what's the probability of transmissions. So in fact, they're doing a gradient update on an estimate of their utility function, the utility function gradient in particular. I can just be quiet for a while, listen, this is the probability of transmissions around me, and now I can compute this term. And so then the results in this paper is they motivate this utility design based on throughput and fairness considerations. They show that it has a unique Nash equilibrium, and they show that this approximate gradient play, gradient update rule does in fact converge to that Nash equilibrium, and then they show various simulations to reflect the performance of the overall approach. So that's going through the game theory playbook. Design utility functions, implement an adaptive law, and then ensuing analysis or simulation studies. We talked about the file storage problem. So remember the file storage problem. I'm a local server. I need to service my own population. If I keep files locally, it's cheap to store. If I get a file request of a file that I don't have, I can ask my neighbor for a little bit more money to make that request. But if I have a file that, if there's a file request that I don't have locally and my neighbor doesn't have it, then for a little bit more cost, then I can get it from a central repository. So that's the setup. The environment here is my own population. How frequently are people in my population asking for different files? I actually don't know that. But again, what I can do is I can go online and measure it. Okay, so you see there's something that's common to these problems is that there's an environment that's unknown a priori. What was the environment in the previous case? The topology of the network. What's the environment in this case? What are the file demands of my own population? But if once I go to implement our learning rules, then we can kind of try to estimate these environmental factors online. So what is their utility function? Here it's represented in terms of a cost function. So everywhere I've been saying maximize, we minimize, but it's the same thing. So my cost function is what's the cost of the local file requests, and that depends on the frequency of the file requests, plus what's the cost of the file requests that I don't have but my neighbors have, plus what's the cost of file requests that I don't have and my neighbors don't have that I have to get from the central storage. Okay, my cost is a combination of these three, and you see that my cost depends on the file requests from my own population. Okay, it also depends on the storage of my neighbors, and that's the game. Remember, my utility or my cost depends on my choices and the choices of others. And so it depends on my choices, the choices of others, and the environment. And the environment is the frequency of file requests. They implement something called, they implement, instead of, we talked about a best response rule, they implement something called a better response rule. Okay, the better response rule is do something today that's better than what I was doing yesterday. Not necessarily the best action as compared to others, compared to what I was doing yesterday, but just something better. Just do a little bit of an improvement. They show in this paper that the resulting game has a finite improvement property. And remember we talked about that, and what does that mean? That means that better replies will terminate to a Nash equilibrium. The problem is that I don't know how to do a better reply because these file frequencies, I don't know them, but I can estimate them. And then they do an analysis to say, what if I'm estimating these things with some uncertainty, what's going to happen? It's going to be a stochastic evolution because I'm doing estimation with uncertainty, and then they do a little bit more analysis to assess that. But you see, it's the playbook. Define utility functions, implement some learning rule. That learning rule is going to work for a particular structure game. They show that their game has the finite improvement property. It converges to Nash equilibrium, but I have to do some modification because I don't really know my own utility. And that's an important thing to talk about, is that we can write down the utility of an agent, but really an agent doesn't know their own utility in the following sense. So, when you commute, okay, I guess commuting is not a big deal in Halmstad because it's so peaceful, and so I lived in Los Angeles for a while, and commuting is a big deal in Los Angeles, and all the roads are bad. So when I travel from home to work, or from work to home, I can measure how much time it took. Okay, that's my utility function. The time that it takes for me to travel. I do not have a function that expresses the time to travel as a function of the cars, the time of day, all of that stuff. I do not have a closed form expression for my utility. I can measure my utility on the spot, but I don't have a functional form for my utility. So even though it's my utility, that doesn't mean that I have it as a function and I can compute gradients or optimize or things like that. Generally, it's all online. I can measure it, but I don't have a functional form. And a lot of these problems are of that sort, that agents or our nodes can measure things, but they don't have functional forms to evaluate their own utilities.
But can't I encapsulate some function to describe my data?
Try it. I mean, how many cars are on the road? Okay, try it, yeah. So you can try to do an estimate, sure. Okay, but I don't know, it's unclear if you really want to. Okay.
But maybe if you measure, things in a short duration, maybe you can estimate the gradient.
Maybe, yeah. Think of it, for example, and this is not my area, but say, for example, in data networks. So you have the notion of a routing table. Okay, a routing table is I get a message, it has a destination. Which one of my neighbors should I pass it along to? And then we're interested in the overall delay from my message going through me to its destination. There's no way we even know the network topology. We're not going to form a function of what is the delay as a function of the routing decisions of everybody in the network. But we can estimate that when I use a particular routing rule, if I get some feedback, then I can try to get some estimates of the delays that I'm experiencing. But we'll never try to actually form this function. Okay. So we can, that's still consistent with measuring the consequences of my current actions, which is different from trying to form an estimate of the utility function. Measuring consequences of current actions, we can do that. Okay, so we're going to talk about some of our own related work, and we'll focus on these topics. One is the idea of a distributed efficiency loss. The other is, well, I'm going to actually tell you the algorithm that we used in the video that I showed yesterday, this exploitation exploration algorithm, and I'll mention a bit about utility design. I won't have time to talk about matching problems. What's of interest here is that matching problems show another side of game theory that's not about Nash equilibrium, but about other things. You find that game theory comes in two flavors. There's something called non-cooperative and something called cooperative. And this is in the world of cooperative games. Everything I've been talking about is called non-cooperative games. Okay. Now, the terminology can be confusing because we're using non-cooperative game theory to design algorithms for sensors to cooperate. But that's just the way it goes. Okay. So first I'll talk about distributed efficiency loss. In distributed efficiency loss, the issue is as follows. If we had a central commander that can tell everybody what to do, then the central commander can kind of order what it wants to see to optimize its own criterion. Okay. Now, if instead of a central commander, we're going to give the individual agents their own incentives, and then let them self-organize, well, they might not do what the central commander would have liked them to do. Okay, and this is a nice example. This is a very well-known example called the brace paradox. So for now, ignore this link in the middle. Okay, and so what we have here, we have a whole continuum of agents. Okay, think agents, a volume of agents that equals 1. Okay, and we want to let's see, they want to go from the source to their destination, and so the agents need to split. What fraction is going to take the high road, and what fraction is going to take the low road? Okay? And this percentage sign means that the delay, the congestion that they experience depends on the fraction. Okay? So this means say it's a big road with lots of lanes, so it doesn't depend on the fraction. Okay? But this one depends on the fraction. So if we looked at the congestion that people who take the high road will experience, what fraction takes the high road times h plus 1. This is the number of users or the volume of users. This is the congestion that they experience and overall congestion that they experience on leg 1 and leg 2. And then what fraction take the low road times, let me write it as 1 plus L, because they meet the 1 first and then the L first. And of course, we have H plus L equals 1 because the population sums to 1. Okay? Now, each high road user is only worried about their congestion, and each low road user is only worried about their congestion. Then what's going to happen, as we mentioned last time, is how do you think this traffic will play itself out? It'll be that the high road and the low road have equal congestion, right? Because if it's cheaper over there, then I'll migrate to over there. So once it levels out, then they have equal congestion. Okay, and if we add these two up, that's the overall congestion. So if selfish agents self-organize, half of them will take the high road and half of them will take the low road. Okay, and if a central commander is interested in minimizing overall congestion, guess what a central commander will do? Same thing. Have half of them take the high road and half of them take the low road. You can formulate this as an optimization and solve it, and you'll find that 50-50 is the optimal. Now, here's the Bayes paradox. Someone says, let's build a superhighway. And let's build a superhighway between nodes A and B, and it's such a superhighway that the congestion is 0. Okay, so it's free. One can transport between A and B. So now you are an individual. Which road would you take? You can go to, once you go to A, you can switch to B. Once you go to B, you can switch to A. So it's inconsequential. You're only worried about the congestion here. So which has less congestion? Top. What does it depend on? Nothing. It always has less congestion, right? So you're always going to take this path. And then what are you going to do? Switch. Okay. So what happened by putting, this is the Bayes paradox, what happened when we put in an extra road? What is the overall congestion? It's everybody takes the high road, and then everybody switches to the low road. Okay, and it turns out that the overall congestion is worse with the new road. Okay, so when individuals make their own decisions, when we added the new road, the overall congestion was worse. So then the central commander says, I'm sorry, I messed up. I shouldn't have put that new road. Please ignore the road. Okay? And then the good citizens will ignore the road. Now, what happens? Suppose everybody else is following the rules. What would you do? Hey, I'm going to cheat. Okay? I'm going to, because most everybody else is following the rules. This is 1 versus 1/2. I'll cheat a little bit, and then I'll cheat. And what happens when everybody thinks in terms of cheating? We switch back to the inefficient configuration. Okay, so distributed agents making their own decisions can go to a configuration that is not what the centralized planner would have liked to have seen. Okay? And the paradox part of this example is that came from adding a road. Adding a road can worsen congestion. So this kind of phenomena has been investigated in the recent game theory literature, and it's been called the price of something. Okay? In particular, the terms that have been used is called price of anarchy and price of stability. They're, the marketing department was involved in these terms, but let's define what they mean. Okay? So here's the price of anarchy. We'd like to know what is, actually this is in terms of costs, not in terms of rewards. So think of G as a cost. Okay? What is the cost at a Nash equilibrium versus what is the cost that a central commander would experience if the central commander could order everybody what to do? The bigger this ratio is, the worse off we are. Because this says that self-organizing agents might have a larger cost than what a central commander would do. Which Nash equilibrium, because there might be lots of Nash equilibria, pick the worst one. Okay? So what is the worst case Nash equilibrium outcome versus what a central commander would have done? And that's called the price of anarchy. Then there's the price of stability, which is more optimistic. What is the best case Nash equilibrium versus what a central commander would have done? Both the price of anarchy and the price of stability are always bigger than 1, and you can see that 1 is bigger than the price of stability, which is smaller than the price of stability, which is smaller than the price of anarchy. Okay? This is worst case Nash equilibrium. This is best case Nash equilibrium. Okay? What does it mean for the price of stability to equal 1? That means there's a Nash equilibrium somewhere in there that represents what the central commander would have done. That doesn't mean the agents will find it, but it's there. And then a price of anarchy being large means that our agents might get stuck at a very inefficient configuration as compared to what a central commander would have done. Here's an illustration of price of anarchy and price of stability. It's again a commuting game. And the way it goes is as follows. Everybody can commute from their home to town for a cost of 1. Or if they, instead of going commuting on my own, we can take the bus. But how much does the bus cost? The bus costs k divided by the number of users. So if there's only 1 user taking the bus, that user has to pay for the bus entirely. K divided by 1. If there's 10 users taking the bus, it's K divided by 10 is the cost. They share the cost of carpooling or taking the bus. Okay, let's call it carpooling instead. Okay, the more that take the carpool, the less it costs. This game has 2 Nash equilibria. One Nash equilibrium is everybody commutes by themselves. Why is that a Nash equilibrium? Because remember, remember Nash equilibrium said unilateral deviations, not group deviations. So if I'm commuting by myself, and if everybody's commuting by themselves, I can say, should I carpool? Well, then I'm footing the whole cost of the carpooling. I'm not going to do it. Okay? So each one of these solo commuters will not take carpool. There's another Nash equilibrium, and in that other Nash equilibrium, everybody carpools. Okay? And when everybody carpools, they can say, should I switch to being a solo commuter? Well, right now, what's my cost? My cost is K over N, and K over N in our setup is less than 1. So I'm not going to switch, because then it's more costly to go it alone. So this game has 2 Nash equilibria, one where nobody carpools and one where everybody carpools. And so the price of stability is actually 1. If the central commander could minimize overall congestion, the central commander would say everybody carpool. Okay, so that the Nash equilibrium is what the central commander would do, but it also has a price of anarchy.
Is the price of anarchy 1?
No, it's this one.
Sorry.
Yeah, price of anarchy it's more. Yeah. The price of anarchy, it's going to grow with the number of users. In this case, it grows linearly with the number of users, which is gentle growth, but it grows linearly, but it does grow with the number of users. So, there's, you can look at this survey paper, Intrinsic Robustness of the Price of Anarchy. There's lots and lots of literature on price of anarchy. What's the price of anarchy for this type of game, that type of game? Does it grow? If it grows, how fast does it grow? What about other solution concepts other than Nash equilibrium? There's a whole kind of culture now for price of anarchy, and you can follow that up. So we're also going to look at that kind of distributed efficiency loss. But what we're going to try to do is we're going to try to use exploration versus exploitation to try to overcome this issue. That if the price of stability is 1, we're going to try to design dynamics so that they avoid this equilibrium and favor the good one. Okay? So let me give some illustrating simulations here. So what's happening here is a coverage problem.
Sorry,
Yes?
to understand the problem. So do you know that always price of stability is lower? So you should always aim for this strategy.
Yeah.
Okay.
Yeah. Right. Yes. So what we're going to try to do is use stochastics to do equilibrium selection. Yeah, stochastic exploration to do equilibrium selection. And in particular, we're going to construct the utility so that price of stability is 1. Not just lower than price of anarchy, but equals 1. Okay. So here's a coverage problem where some graph, the graph is the environment, so they don't know their environment, and what's going to happen is that A node is considered covered if a sensor is sitting on the node, and it's covered if the sensor's neighbor, if a neighbor of the sensor is sitting on the node. So for example, if I had a sensor sitting here, then the coverage is 1, 2, 3, 4, 5. Okay, where I'm sitting and my neighbors. And we'd like these to evolve. And what we're going to do is best response dynamics, but not actually, it's not fully best response dynamics. It's best perceived response dynamics. What do I mean by that? If I'm sitting here, I really don't know the rest of the graph. I know my nearby nodes, and I'm going to do a best response amongst my nearby nodes. But I don't see the rest of the graph because that's an unknown environment. I only can kind of see what's happening locally. And what happens here is that, well, you have 8 nodes that are just sitting here because they don't have anything better to do. All right, if I'm here, if I'm there, it's the same, so I'm going to be lazy and stay where I am. Okay? And this reaches a deadlock configuration. Now, if we introduce some exploration versus exploitation in a particular way, then there's a deadlock, but what's going to happen here is some nodes are going to say, there's no benefit in moving, but I'm going to move anyway. Sometimes they're going to say, my coverage is worse when I move, but I'm going to move anyway. Okay? And if we balance that exploration part, then we can show analytically that most of the time the agents will be covering the most of the graph. Okay? Why not all of the time? Because we never turn exploration off. Okay? And they don't really remember what they learned. These agents, like I said, they don't maintain a memory of where I've been, and they're not doing building a map. They're not doing any SLAM here. They're just moving along. So to talk about this, I need to introduce. It has different names. Sometimes it's called logit distribution, Gibbs distribution, softmax, but let's let me give an example. 3, 4, 1. Okay, what's the maximum of this vector? 4, all right? Which is the maximizing element? Second element. So instead of saying the second element is the maximizing element, I'm going to say that's the maximizing element, okay? Why are we saying that? Suppose you drew a probability with this distribution. What element would you pick? Second one, because the others have 0 probability of selection. What this is the Gibbs distribution is that we're going to pick the maximum with high probability, and it depends on this underlying variable t, which is not coincidentally called temperature, because we're mimicking simulated annealing here. So 3, 4, 1 is going to be turned into e to the 3 over t, e to the 4 over t, e to the 1 over t, and we have to divide this by, to normalize it so that they all add up to 1. Okay? So let's see what happens when the temperature is huge. Okay? It's 1 over z. When the temperature is huge, like suppose the temperature is, whatever, 100. Okay? E to the 0.03, e to the 0.04, e to the 0.01. These are all approximately equal to 1. So this approximately equals 1/3, 1/3, 1/3. So what happens when the temperature is huge? Pick something at random. Slightly favor the largest element, but pick something at random. Now what happens when the temperature is small? Let's, for example, have t to be 0.1. This is 1 over z, e to the 30, e to the 40, e to the 10. This approximately equals 0, 1, 0. Right? Because e to the 40 is a whole lot bigger than e to the 30. Yeah? So you see when the temperature is large, it picks something at random. When the temperature is small, it strongly favors the maximizer. But there's always a probability of selecting something else, okay, which would be the true max. So sometimes this is called the soft max. but we're going to use the Gibbs distribution. And now here's a learning rule that we're going to make a slight modification of this learning rule so that we can finally do the algorithm that I showed in the video. What is this learning rule? We have a bunch of agents. One agent is picked at random. That agent is allowed to update their action. So then the agent does a what if comparison. Okay. So suppose an agent has 5 actions. Then they're going to say, what is my utility if I use action number 1? What is my utility if I use action number 2? What is my utility if I use action number 5? What does best response dynamics do? It picks the largest one. What does log linear learning do? It picks the largest one according to it executes the Gibbs distribution. Which means if the temperature is large, it just picks a move at random. If the temperature is small, it favors the largest one, but it might explore and pick something smaller. This is so-called log linear learning.
Sorry, but the temperature is supposed to stay constant, or you can change it?
Yeah, we're not going to anneal it to 0. We're going to leave it as constant. Okay, we're going to leave it as constant. So it turns out that one can do a analysis for log linear learning. And for example, we saw this graph yesterday. This is 3 agents, each with 2 moves. What's going to happen is that the agents are just going to be moving all over the place. It's a Markov chain. It will have a steady state behavior. And one can show analytically for potential games, this picture is better, for potential games, suppose that 110 was the largest value of the potential function. What one can show is for small temperature, it's going to spend most of its time here. So for potential games, log linear learning spends most of its time at the maximizer of the potential function. It lingers there. Okay? And that's how we're going to do equilibrium selection. We're going to design a potential game where the maximum of the potential function is where we want the agents to be. We're going to implement a variant of log linear learning, and they're going to spend most of their time at the maximizer of the potential function. Okay, so what's the variance? What's the variant of log linear learning? Let me explain it in a picture. Okay. Here's the graph. Sensors need to decide where to go, right? So what are the different choices of a sensor? My different locations. How many locations do we have here? About, 40 locations. How would log linear learning work? Look at all 40 locations, decide where I should go based on the Gibbs distribution. But we said that agents don't really know this graph. They only know what's around them locally. Okay? So if an agent is sitting here, it can decide it doesn't know the rest of the graph. It's not remembering the rest of the graph. It's not building a map of the graph. It's going to make a very simple-minded assessment. Should I stay, or should I go to this neighbor, or should I go to that neighbor? Okay? So my move today is constrained by where I was yesterday. Log linear learning says, look at all 40 options. We need to modify log linear learning because we can't look at all 40 options. So our modification of log linear learning is as follows. This is the modification of log linear learning. Here I am today. I have a small number of options. Pick one of my options. And now I'm only looking at two items. Should I stay where I am, or should I pick that randomly selected option? How am I going to make this choice? I'm going to use the Gibbs distribution to make the choice. So sometimes this is called probe and adjust dynamics. Pick one alternative, that's the probe part, and adjust is pick the better one according to the Gibbs distribution. And then one can show analytically that probe and adjust will, for potential games, spends most of its time at the potential function maximizer. Okay?
So that doesn't seem like the most obvious strategy. I would think you would just look at all your neighbors and then add yourself and then maximize based on those. Why?
Okay, and that's I can tell you in detail why that doesn't work. Okay, just yeah, I have to go through this example, but that doesn't work. It turns out that what you're suggesting is mimic log linear learning over my local choice set. It shifts it shifts where the Markov chain will linger. It can spend its time elsewhere as a result, and I can show you through this example. Okay. Yes.
Couldn't you change the temperature based on your perception of the equilibrium? So if you sense that you're close enough to the equilibrium, then you increase the temperature. Right.
Yeah. So decreasing makes it more sticky and more like a maximizing. Yeah. Yeah, but then somehow we'd have to have a global awareness of how well we're doing.
Yeah, but maybe locally, but by your perception.
Yeah. So then, if you're suggesting that every agent keeps its own temperature, and if it feels it's doing well locally, yeah, that's a possibility. Another possibility, I mean, if we want to completely mimic simulated annealing, is that agents would keep an open loop scheduling, temperature scheduling, and gradually reduce the temperature at some very slow rate. But that's kind of goes against the perpetual adaptation philosophy. So you could have a performance-dependent temperature. We haven't pursued that. But the issue is that how do you assess global performance locally? Yeah. All right, so the analysis, just to mention the analysis, what it kind of looks like, is that, here we have a three-state Markov chain. If it's in state 1, it can escape with epsilon squared probability. If it's in state 2, it can escape with epsilon probability. If it's in state 3, it can escape with epsilon probability. So no matter where it is, it can escape. But when epsilon is small, where do you think it's going to spend most of its time? In state 1. Because it's really hard to escape. That's epsilon squared probability to escape as opposed to epsilon. So as epsilon goes to 0, these nodes become sticky, but that one becomes very sticky. Okay, and that's the nature of the analysis that supports this. So I'll just, and that's how we came to this video. What these agents are doing is binary log linear learning. And not only are they doing bilinear log linear learning, they're doing it in a drifting environment. So the environment is changing, and they just keep on doing binary log linear learning to track the potential function maximizer. I'll end this with mentioning of how we design the utility, and then I'll just close for questions. Okay. So how are we designing the utility? There are many considerations in designing the utility. One is we would like the game to have a particular structure so we know our learning algorithm works. For example, the finite improvement property is desirable. If we're not going to do stochastic exploration, then we're going to be worried about what's the resulting price of anarchy, what's the resulting price of stability. So the way that we're designing our utility here is what's called the marginal contribution utility. Now, for a US audience, this is also the one who suggested this from the CS community, also calls this the Wonderful Life utility. I don't know if you've seen this movie, It's a Wonderful Life. So a person is having a hard time. He says, I wish I'd never been born. And then he gets to see what the world would be like if he was never born. Okay, and then he says, it's a feel-good ending. He says, oh, I guess it's better off that I'm in the world. And then money saves the day, by the way. But he realizes he wants to stay before he got the money. I guess that's part of the message, too. All right, so what is the marginal contribution utility? I'm going to incentivize an agent in this way. What's the world score with me in the world? Minus what's the world score with me gone? Okay, what am I contributing to the world score? So how does this manifest itself with coverage problems? So suppose, say, I'm a node, there's a shared node, you're a node. Who's covering this node? Both of us. Who gets credit for it? Neither of us. Because if I disappeared, it's still covered. Okay. So this marginal contribution utility says you only get credit for the coverage that you're doing without any help. If someone else is covering the same node, nobody gets credit for that node. And it turns out that marginal contribution utility, it can be evaluated locally. because I can just see, here's my neighborhood. What if I disappeared? What's still covered in my neighborhood? It induces a potential game. That's also good news. And guess what's the potential function? This global score. And now, since that's a potential function, when we apply log linear learning or bilinear log linear learning, we're going to linger at the maximizer of the potential function. And we cook the books so that the maximizer of the potential function is the global score. Okay, and there's a lot of literature on utility design and incentive design and various considerations, but this is a very straightforward one. And so here I have some other examples of utility design. I'll just skip those. And we didn't have time for matching. And actually, I'll leave it here. So we talked about the prescriptive agenda. We mentioned price of anarchy and price of stability. We looked at log linear learning and stochastic exploration. We mentioned the marginal contribution utility. And there's lots of references, and I can send you these slides for further reading, both in Foundations of Game Theory and in the extensive literature on learning in games, and then its application to multi-agent systems. So, thank you.
Questions?
It was one of the vehicles that kept that was never in the covered area.
Mhm.
So didn't its utility function always stay 0? So why did it keep the side when it tried to cover something? Does it take that role to stay outside?
Because with this distribution, then there's always going to be a probability that it does something suboptimal, number one. Number two, if I'm completely outside of the hot zone, then my utility is 0, as you pointed out. And if we apply this, my utility is 0 no matter where I go. What is it going to do? It's just going to do a random walk. So once I'm completely outside the hot zone, regardless of the temperature, because it's 0, 0, 0, I'm going to do a random walk. And then once I find something hot, I will favor it. But now that depends on the temperature, the degree to which I favor it. You had a question?
All right. During this lecture, you mentioned cost function that is equals to local cost plus regional cost.
That was for the data storage problem. Yes.
Yeah, but these costs are multiplied with the constants.
Yes.
Which is, I think it's a step rate or.
And no, those constants were the. Oh, there was the. Let me bring up the slide. There was two parts to that. These constants, alpha, beta, and gamma, just are alpha is smaller than beta is smaller than gamma. It just represents, this is how much it costs to keep a file locally. This is how much it costs to get it from my neighbor. And this is how much it costs to get it from the central storage. The W's are the frequencies of my own population. So how you can think of this is the retrieval cost for my own population. Alpha means it's local. And then the summation of W is how frequently am I getting each of these files.
So nothing to deal with the learning rate.
No. This is just formulation of the game, not the learning on the game. So remember in the playbook, we start off with cost functions / utility functions, then we implement the learning rule. Okay. This is just setting up the game.
Right.
Is there any results regarding how quickly one get close to the optimal?
Yeah. So there's a lot of results there, and there's some good news and a lot of bad news. Okay, and in worst case, it can. So at the end of the day, I mean, if we're trying to solve maximize G, that's an optimization problem, and we're trying to solve it in a specific way, but we inherit the computational complexity that maximizing G would have had in the first place. So there's a lot of there's some results who are saying that if you want to approximately optimize, then you can get there quickly in certain situations. If you want to truly optimize, it takes a long time in very large scale situations. If you want to abandon Nash equilibria and look at other kinds of concepts, such as correlated equilibria, then you can get to a correlated equilibrium quickly. But amongst the correlated, the picture looks like this. You know, here's the set of Nash equilibria, and then here's the set of correlated equilibria, okay, which is a superset of Nash equilibria. You can get to this set quickly, but then you might drift within this set. Drifting within that set might be good or might be bad. It depends. If we'd like to do equilibrium selection, I want this correlated equilibrium in particular, that might take a long time. So the results are all over the place. But generally, if one looks at you know, the worst case scenarios, then it's bad news across the board. And so really what we're looking at is for our particular applications is a good enough. But worst case news is generally bad.
Any other questions?
Yes?
Okay, I have another question in log linear learning.
Yes?
You said that every node has a distribution.
The distribution that with which it selects its next action depends on its utility for that action, and its utility for that action depends on the actions of others.
So is this distribution given, or?
Yeah. So suppose the agent has 3 choices, A, B, and C. Okay. Then I'm going to look at the utility of agent I under choice A. Well, yeah, B and C. I'm using now the letter A twice, so I don't want to do that. Alpha, beta, gamma. Under choice alpha, which depends on the actions of other agents. And I'm going to look at the utility of agent I under choice beta, which depends on the actions of other agents, and gamma, which depends on the actions of other agents. This is a vector. Now, best response is pick the largest one. Log linear learning is form the Gibbs distribution and then make a random selection according to the Gibbs distribution. And everybody's using the Gibbs distribution, okay, with the same temperature.
What is the best distribution in this case?
In terms of, actually that's a very interesting thing that we're looking at right now, is that using the Gibbs distribution leads to, has the following property, that it will spend most of its time at the potential function maximizer in steady state. There are other distributions that they could use that have the same property. In steady state, they spend most of their time at the potential function maximizer. So a question we would like to answer, and it's related to this rate of convergence. Instead of asking, okay, you might have some behavior that looks like this, or some behavior that looks like this. All right? They both have kind of, let's say this is the global score. They both have the same steady state global score. One is lower but gets there sooner. One jumps up faster but gets there later. We'd like to have tools to assess this kind of comparison. So instead of saying what happens in steady state, let's say what happens in different time scales, and maybe that's a better model of implementing this algorithm. Because by the time it gets to steady state, either A, the environment has changed, or B, we're all dead. Okay, and we'd like to have something in the near term that says that's a better model of the behavior. So when you say what's the best one, it depends on the metric. And one metric that we're trying to understand is what is the near-term or mid-term behavior of the induced Markov chain as opposed to the stationary behavior, because the stationary behaviors of the two are the same.
Any other questions? So I have a final question. It was very nice to see the robot example at the end, and it reminds us of maybe some creatures performing a natural function in a swarm, for example. And at the very beginning of the lectures, you mentioned the transition from the descriptive role to the prescriptive role. Tying the loop, are there examples where these models are a nice fit to swarm behaviors, for example, appearing in nature? And do these give some insights about things like, such as the choice of distributions that various agents in a large group might be using?
There has been some work. I haven't pursued that myself. There has been some work trying to turn the loop in that way. We have closed the loop in a different way. We've shown how some ideas from control theory can help address unresolved questions in game theory for a descriptive part. And I can, I didn't talk about that here. Now, there is a line of game theory where that has been mainly the descriptive discussion, where things like oscillation. So as control people, remember your question yesterday, you said one is better than the other because it converged.
That's
control
right.
people want to see convergence, and when we don't see convergence, we feel uncomfortable. But there are kind of models where oscillations are natural. So, for example, rock paper scissors, we think of it as a game. But there's one example that's brought up frequently in nature. Is there's within a species there are three types of behaviors of the lizards. So one type of lizard has a one-to-one mating, okay, and another has a one-to-many mating. And then a third type has a 1-to-0, okay, just looks for opportunities, okay. So the 1-to-0 can infiltrate the 1-to-many, okay. Think of this as rock, paper, scissors. The 1-to-0 can infiltrate the 1-to-many because the 1-to-many is too hard of a job to protect their mates. The 1-to-many does better than to 1-to-1. Because it has more mating opportunities, but the 1-to-1 does better than the 1-to-0 because it has one mate and can guard it effectively. So you have this kind of rock, paper, scissor triangular dependency, and you can see evolving variations in the populations. So there has been, there's a line of game theory called evolutionary game theory that tries to do that, and they end up analyzing dynamical systems, which is why controls ideas might help for evolutionary game theory, and in fact we have looked at that. But using kind of these simple micro models to analyze or to try to kind of reverse engineer swarm behavior, I wouldn't be surprised if people have looked into that, but I'm not aware of the literature.
Very cool. Any other questions? Thank you very much, Jeff. And since this is the last lecture, a small gift from our university.
Thank you very much.